So in the previous lecture, we discussed about paramagnetic effects, and where the spin of the electron, we associated a dipole moment to the spin of the electron. Now, as you know, in addition to the spin, electrons also revolve around the nucleus. Okay, so they have a orbital motion. Now, this orbital motion can also be thought like a current loop. So here you may be wondering, electron is a discrete charge, right? So like how would that constitute a steady current, so as to say? Now for that you should keep in mind the fact that the time period. So I mean, let me just give you some value. So let's consider a simplified system of a circular orbit of radius r. Now the time period for this circuit, for this circular orbit, will be 2 pi r by v, where v is the velocity. So 2 pi r is your circumference. So, and so the time period, the time taken to complete one revolution will be 2 pi r divided by the velocity. Now, what happens is that this time period is extremely small, extremely short. So, of the order of 10 to the power minus 16 seconds for a hydrogen atom in ground state. Now, because the time period is very short, what you have here is, you can think this electron, and because I mean, time period is so short, you can think of this as a steady current circuit, current loop, purely because of the fact that time period is very short. Of course, technically you cannot call it, I cannot really have a current loop with one charge moving, but effectively, because it revolves very fast around the nucleus, so you can think of it a tiny current loop. Now if you are convinced with that, now you can look at what is the current there. So the current is nothing but your charge over time, and that is charge is your minus c, and the time period is t, what we calculate 2 pi r by v. So if you plug back those things, you have the current as ev by 2 pi r. Now if you have a current loop, you will have a dipole associated with it. So the dipole which is associated with this sort of current is nothing but I multiplied by the area. Okay, so that is your current, and that is, so I mean, now we are in a position to define dipole moment associated with the orbital motion of electron, and that is nothing but minus 1 over 2 EVR z cap. So if you want to see it in some sort of a diagram, so you have your electrons which is moving like in a circular orbit. So my drawing is not that good, and you have, this is my, you can think of this as your z cap, and that's your velocity of electrons. So, and that's your radius r. Okay, now the magnetic dipole moment will be minus of z cap, so that's your m. Okay, so that's your geometry here. So an electron is revolving here, minus. Okay, so now that you have a dipole, now if you put this in a magnetic field, again, for simplicity, we can imagine the magnetic field along the g direction. So now we can imagine a magnetic field along the g direction. So now imagine we have a magnetic field like that. So with that, now when there is no magnetic field, you can write the force balance equation like this. So you have this Coulomb force balanced by the centripetal accelerations. So that is your v square by r, right? So, and then so if you want to write the equation, the force balance, which will be like 1 over 4 pi epsilon 0 e square by r square Okay, so that is your Coulomb force, and then that's your ME V square by R. Okay, that's for the B square over R is the centripetal acceleration. Now, what happens if you now add the magnetic field? So now, as I told, so let's add the magnetic field along Z direction. So B is along Z cap and uniform. Okay, so if you do that, so now you have a force component due to the magnetic field, and that is nothing but your E. So now the velocity changes. Okay, so now let's see, think that when you apply a magnetic field, there is a change in the velocity. Now, why does it happen? So I should have mentioned. So now, because you have an orbital dipole moment associated with this orbital velocity of the electron, so this will experience a torque in a magnetic field. However, it is very difficult to tilt the orbit. Okay, you should now know this, that it's very difficult to tilt the orbit, and then how will you reduce the torque? So one way to reduce the torque is to change its velocity. Depending upon the orientation of the B, you can either increase or decrease your velocity V, which will effectively reduce the torque. So that's why if you have a magnetic field B, your velocity now has changed. So now we'll write that the V prime. Okay. So that's why I have written here V prime. Now you have a magnetic force component. So B is perpendicular to Z. So you will have this component E V prime B. Okay. Because you will have this Q B cross B, right? So that effectively gives you this component. So now you rearrange them. So your this one is nothing but your ME V square by R that you replace here. E V prime B remains there, and then that is balanced by the ME V prime square by R. So you rearrange a little bit, and then you say that my the change in velocity V prime minus B is really small. So if you say that, then this particular term B prime plus B, V prime minus B can be rearranged, and then since delta V is very small, you can effectively write this as only 2 delta V here. Okay. And then if you rearrange, you have delta V will come out as ERB by 2ME. Please check again, check all the algebra here. It's simple. So once you know the change in delta V, now you can write the corresponding dipole moment. What are the change in the dipole moment? And that's your delta M corresponding to delta V. And that turns out to be, because your dipole moment is nothing but, and I have already shown you here, dipole moment is this one, where I have seen, yeah, here. So the dipole moment is nothing but half EV R Z cap. So your delta M now, because your now V has changed with an amount delta V, so your delta M effectively changes with minus half E delta V R Z cap. So now for delta V, you can replace this one, and then you do the calculation. So you will have eventually delta M as minus E square R square 4ME. Okay, so what does it mean? It means that when you have an external magnetic field B, your dipole moment changes in an opposite way. There is a negative sign here. Okay, so which means the change in M, that's very important now. The change in M is opposite to B, or your magnetization is now opposite to the applied field. Now, as again, due to random orientation, these orbital dipole moments cancel out in general. So you will have net effect is 0, but however, in presence of your external field, these dipoles are modified. Modified in the sense there is a change which happens opposite to B. And this is essentially the mechanics which is responsible for diamagnetism. So the magnetization is opposing the applied field. Now this diamagnetism is an universal phenomenon. Okay, unlike paramagnetism, which needed a unpaired electron to have bigger spins come with pairs. However, orbital motions, there are no such things. So, orbital motions you will have. That's why diamagnetism is an universal phenomenon. However, the catch is that it is a very weak effect, much more weaker than the paramagnetism. So, in other words, although diamagnetism will be present in all materials, but wherever there is a paramagnetic effect, this will dominate. So, therefore, your diamagnetism you can only observe only when there are no paramagnetic effects in the material, and that can only happen only when there are even number of electrons. Okay, if there are even number of electrons, your paramagnetic effects are not observed there, and that time only you can observe the diamagnetism. Okay. Okay, so I will end this short lecture here. So here we discussed about the effect of diamagnetism, what is the origin of diamagnetism. In the next lecture, we will go into more detail and understand what is a field due to the magnetized object.